Hey math fans, Alex here to you today with a problem from the 1995 Putnam Exam. This was problem A1, and it says the following. Let S be a set of real numbers which is closed under multiplication. That is, if you have two elements A and B in S, then the product AB is also in S. Let T and U be disjoint subsets of S whose union is S. Given the product of any three elements of T is in T, and the product of any three elements of U is in U, show at least one of the two subsets, either T or U, is closed under multiplication. Okay, so that sounds like a lot of information. So the first thing to realize is that you have the whole real number system, and we're saying that S is a subset of that. Okay, so you could have a couple real numbers here, real number there, subset there, and all of those together make up S. So the important part to realize is that S has associativity and commutativity. So S, since S is a subset of R, we know that S is associative and commutative under multiplication. Okay, it just inherits those. I had a professor once say that in group theory, at least, associativity is like oxygen. It's essential for life, but many people forget that it exists. Okay, next up, we know that the subset is closed under multiplication. So if you have elements A and B that are in S, then the product A times B will also be an S. This is usually what happens in the real numbers, right? If you take any two real numbers like -7 and pi and multiply them, you're going to get a real number. Okay, so it almost inherits that from the real numbers as well. And now for the fun part. So let T and U be disjoint subsets of S whose union is S. Okay, so this portion right here, if you draw a picture, let this be S, and what we're saying is that T and U are disjoint subsets of S. So that means that there's no overlap. If an element is in T, it is not in U, and vice versa. And the union, or the combination of T and U, make up the entirety of S. So for instance, for the integers, I could say the integers have the set of all even numbers and the set of all odd numbers, and those are disjoint because a number can't be even or odd, and then the union of those is also the set of all integers. Okay, so I like this picture. And it says, given that the product of any three elements of T is in T, and the product of any three elements in U is in U, we have to show that it's closed under two elements being multiplied. Okay, so if three elements multiply together is in U, I call that being closed under ternary multiplication instead of binary. Okay, but that's just a term, it doesn't really matter. Okay, so by the way, if you didn't notice, T and U, by definition, form a partition. A partition S. Okay, that's what the word partition means. Okay, and the first thing that I tried is I took three elements of T, maybe call it T1, T2, and T3, and I know that if you multiply them together, you're in T, for sure. Any three elements in T multiplied together is in T, and likewise, any three elements U1, U2, U3 multiplied together, that's in U. So what I tried doing at first is I tried multiplying these elements together, okay, T1, T2, T3, U1, U2, U3. And we know that since this is an element of T, that's a subset of S. Okay, so this has to be an element of S. Likewise, this product has to be an S. And S is closed under multiplication, so this six-tuple product is also an S. Okay, so I tried using that kind of logic to show that the product of, two of these elements has to be in T. But I didn't really get anywhere with that. I didn't get anywhere in that. So what I did instead is I simplified the problem by a lot. Okay, so consider what we're trying to prove is at least one of the two subsets T and U is closed under multiplication. Okay, so you have to prove at least one of something. So the common way to prove that is to prove it using contradiction and to suppose that none of them is closed under multiplication. But actually, if you only have to show one or two of something, at least one of the two subsets, then another common thing that's done is to show that if you have two things and you're just trying to show that one of the statements is true, show that this one, if this isn't true, this has to be true. Okay? So what we're going to do is assume, so this is now going to start the proof. So assume that T, for example, is not closed under multiplication. And then we're going to show that U has to be closed under multiplication of two elements. Okay? What does it mean to not be closed under multiplication? Well, that means that there has to exist two elements in T, where if you multiply them together, you're not in T. That doesn't mean that if you take any two elements, the product isn't in T. You can certainly find exceptions to that. It just means you can find one pair of numbers whose product lies elsewhere. Okay, so I'm going to go ahead and let those pair of numbers, we'll label it T sub I, perhaps, and T sub J, and we're going to let those be in T such that Ti times Tj is not in T. Okay, well, since Ti and Tj is not in T, and since these are disjoint, that means that it has to be in U. Okay, assuming that they're elements of S, if you're not in T, you have to be in U. Okay, so as a consequence, we have that Ti times Tj is in U. Okay, so if we're assuming T isn't closed under multiplication and we're trying to show that U is, so I'll just write that down. We need to show that U is closed under multiplication. Okay, so what does it mean that U is closed under multiplication? So i.e., we need to show now that any two elements, not that there exists, but we need to show that all arbitrary pairs of elements in U, when multiplied together, stays in U. Okay, so we should say, for all U1 and U2 in U, we have that U1 times U2 is in U. Okay, so that's what we're trying to show. So what I do is I go ahead and let maybe we'll call it UK and UL be in U, and we're going to let those be arbitrary. That means they could be any elements. I'm not going to number them 1 or 2 because we don't really know if it's even ordered, but we're just going to let those be arbitrary elements of U. Okay. And what we're going to do is we're going to consider the following product. We're going to consider the product Ti, Tj, UK, UL. Let's just talk about that product for a second. What do we know about that product? A couple of things that we know about that product. Number one, it's an S, right? Because S is closed under multiplication. All these are in either T or U, which are both subsets of S. So all these multiplied together, we know for sure that that's an S. Well, that doesn't really help us. But what it does tell us is that if it's an S, this product is either in T or it's in U. Okay, the other thing that I'm going to do is note that Ti times Tj, this guy right here, according to our assumption right here, we're assuming that that specific combination of elements, when multiplied together, isn't in T, so this is in U. All right? And now I also have another element of U, and a third element of U. So I have 3 elements that are technically in U multiplied together, and by our assumption, we are assuming that the product of any 3 elements of U is in U. So we're going to use that assumption to say that this element has to be in U. It's the product of 3 elements that are in U. The first one, we artificially created it because we're assuming T isn't closed under binary multiplication. Okay, so that element has to be in U. And then we have these 2 singleton elements that have to be in U by assumption. Okay, so what we have is we're trying to show that, and again, I'm just going to kind of do this in light red so you know our goals. So again, what are we trying to show? We need to show that UK times UL, since those were arbitrary elements, we're trying to show that the product is definitely in U. So now is where we're going to prove using contradiction. Okay, so I'm doing this proof in black. So by way of contradiction, go ahead and assume that UK times UL is in T. Okay? But then something I would like to point out is consider the product again, TI, TJ, UK, UL, and play the exact same game, but just kind of reverse things a little bit. Okay, so now we have something which we've assumed by contradiction is in T. So this element is in T, right? And then by the same token, this element is in T by assumption, and that element is in T by assumption. So now we have 3 elements that are all in T, and the product of any 3 elements in T must be in T. So this element has to be in T. Okay, but do you see the contradiction there? Which is a contradiction because the subsets U and T are disjoint, which means if this is in U, it cannot, for sure, cannot be in T. And we just showed, well, if this is true, then it's in T, which can't happen, which means the original assumption cannot happen. Thus, we have that UK times UL is in U, and since UK and UL were arbitrary elements of U, that means there were any 2 elements, arbitrary elements. This is enough to show that U is closed under, we'll say, binary products. All right, that concludes the proof. Hope that was helpful, and have a great rest of your day.